Hmm. All right, folks. Today, what we want to focus on is trends in atomic properties. All right, so we went over the definitions of these trends in last night's video. So just a quick recap of that. The three trends that we want to look at are atomic size, which is simply the radius of the atom. So in other words, we want to see whether or not an atom is going to get bigger or smaller as we move around the periodic table from left to right or top to bottom. The second thing we want to look at is ionization energy. And the definition of ionization energy is essentially the energy required to remove 1 mole of electrons from a neutral element in its gaseous phase. Okay, so I sort of show a little reaction that gives you that. So notice the electrons being ripped away from the atom to leave a positively charged cation there. And then the electron affinity is essentially the opposite of that. I'm going to take 1 mole of a given element in the gas phase, and I'm going to force a mole of electrons into it to give me the anion, or the X1 minus ion there. And X there just represents a generic element. Okay, so all these things happen in the gaseous phase. So we want to see what the trends look like as we move around the periodic table for all three of these things. All right, so what we want to do is look at size first. So that's going to be our first trend to investigate. So really, again, what we're talking about here is the measured radius of the atom. So what I'm going to do is I'm going to give you some characteristic elements in the periodic table, both across a row and down a column. And I'm going to give you some radii so we can sort of see what the trends look like. So we'll take row 2, starting with lithium, moving across to beryllium, then boron, and we got carbon, nitrogen, oxygen, and fluorine. Then moving down, we'll go to sodium and potassium. This is all group 1A stuff. And we'll go as far as rubidium. That'll be enough for us to see a trend. All right, so again, I'm looking at picometer radii here. Okay, so these are going to be in terms of picometers. So lithium is 152. Beryllium is 111. Boron's 88. Carbon 77, nitrogen 75, oxygen is 73, and fluorine is 71. Now moving down the column, sodium is 186, potassium is going to be 227, and rubidium will be 248. All right, so again, we can take a look at trends here. So the first trend I want to investigate is what happens as we move from left to right across the periodic table. As you can tell here, the atomic radius is getting smaller. It's decreasing. So I see a decrease as we move left to right across a row. Okay, what happens as we move top to bottom down the column? Well, we see there that we're getting an increase in the atomic radius. Okay, so it gets smaller in one direction, bigger in the other direction. Okay, so the question now is, now that we see this trend, we want to see if we can actually explain it based upon the electron configuration. So in other words, let's think about where the electrons are going and why the trend would be as it is. Okay, so the things that the trend or trends depend upon are the following. So the first thing is the principal energy level of the outermost electrons. Okay, so again, what's really defining the size of the atom? Well, it's really going to be what orbits or orbitals those outermost electrons happen to be in, right? So as we inhabit more of the outermost orbits or orbitals, the atom ought to be getting bigger. All right, so basically it's the principal energy level of the outermost electrons, or the valence electrons. All right, so for example, let's take a look at what's happening as we go from left to right. So if I go from lithium across to fluorine, right, what am I doing? Well, I'm filling the second principal energy level, right? So any of those, what I'm doing is I'm dealing with the n = 2 level there, right? So I have to get through the N=1 level to get to helium, and then lithium through fluorine. What I'm doing is I'm filling that second principal energy level. Okay, so I'm putting in 2 s electrons and then a set of 2 p's. Okay, so am I changing the principal energy level there as I go across? No, I'm not. I'm filling the same principal energy level. Okay, so what about going from lithium down to rubidium? Now notice what's happening there. I'm filling a new principal energy level. So if I'm at the N=2 for lithium, by the time I get down to sodium, I'm dealing with N=3. Potassium, I'm dealing with N=4. Rubidium, I believe I'm dealing with N=5. Okay, so notice that as we move down the column, I'm introducing a new principal energy level. Now that one's easy, right, guys? Because as you go to a new principal energy level, what do you know about the size of the atom? Well, it ought to get bigger, right? Because the N=3 level is further out than the N=2. The N=4 is further out than the 3. The N=5 is further out than the 4. Okay, think back to the Bohr model there. That's probably the easiest way to look at it. Okay, so anytime you're introducing a new principal energy level, you would expect those outermost electrons to get farther and farther from the nucleus. But again, if you're not introducing a new principal energy level, in other words, you're going across, okay, the atom's actually going to get smaller for reasons we're about to explain. Okay, so everybody see essentially what that dependence kind of comes from. Second thing is nuclear charge. Okay, so remember that the nucleus has a positive charge and that the electron carries a negative charge. Now, what ends up happening? Well, as we increase the nuclear charge, it's going to pull the electron in closer to the nucleus. And what's that going to do? It's going to make the atom look smaller, isn't it? Okay, so this is going to come into play as we move across the row. Okay, looking at lithium through fluorine. What's happening there? Well, again, we're introducing an electron in each case, right? But we're introducing it to the same principal energy level. But what else are we doing? Well, as we move across, we're also introducing a new proton to the nucleus. So what's happening to the nuclear charge as I go across? Well, it's getting bigger, right? Because I'm introducing a new proton with each element. But because I'm introducing the electron to the same principal energy level, okay, that new electron is actually going to feel more pull from the nucleus, okay? So as a result, that's going to cause the atomic size to draw itself in, as I showed there in the little diagram that I just made. Now, that doesn't necessarily explain what's happening as we go down the column though, right? Because think about it, as I go lithium, sodium, potassium, rubidium, I'm introducing more protons there, aren't I? But notice that the atom continues to get bigger. So the thing I have to think about from that point of view is actually what we call shielding of nuclear charge by core electrons. Okay, remember what core electrons are. Okay, those are the ones that are in the inner energy levels, right? Because once we get to that outermost principal energy level, those are the valence electrons. But again, if you think about it, going back up to my little diagram up here, all right, if I'm introducing levels of electrons in here, okay, well, those levels or core electrons there. So basically each one of those things represents an energy level there, if you want to think of it that way, an N value, right? Those electrons are actually going to shield the outermost electrons from the increased nuclear charge that I'm seeing, okay? So they're diluting it in a sense, okay? So that's going to happen and explain why the element continues to get bigger as we move down a column, all right? So yes, the nuclear charge is increasing, but it's being overruled by the shielding of all those core electrons that we have in there, right? So if you look at N=5, for example, it's being shielded by all those electrons that are N=1, N=2, N=3, and N=4. So they're basically using up that charge or diluting that charge, so the N=5 electrons don't feel it as much. So as a result, the atom's going to get bigger. All right, anything there not make sense? Anything there you want me to expound upon? Okay, good. So one other thing I want to mention while I'm here is ionic radius. So what I'm talking about here is when we compare, for example, an element. So if I look at nitrogen by itself, that's going to be at 75 picometers. But if I look at the nitride ion, which is N3 minus, okay, do you think that would get bigger or smaller as I add 3 more electrons to the nitrogen atom to make the nitride ion? Do you think, would you expect the atom to get bigger or smaller in that case? Just a guess. No one wants to go out on a limb on that one?
Smaller?
So why, actually, let me ask, why would you think smaller? Let's see if we can reason this out. You know,
As the nuclear charge increases?
Oh, but wait, does it? So that's actually a really good point you bring up. So think about it. It's nitrogen in each case. Now, what defines the identity of an atom or an element? It's the number of what in the nucleus? It's the protons, right? So whether we have a nitrogen atom or a nitride ion, it's still got the same number of protons in the nucleus. What's increasing? It's the electrons, isn't it? So if I put 3 more electrons in there, but I have the same nuclear charge, okay, I'm having to disperse that nuclear charge amongst more electrons. Okay, so what's that going to do? Make the atom get bigger or smaller if I have to share that amongst more electrons?
Bigger.
Bigger, yes, the atom's going to expand out, and actually by quite a bit. So it turns out the nitride ion is actually 171 picometers. And we can make the same argument going in the other direction, for example, with a metal. So aluminum is 143 picometers. That's just regular aluminum. But if I want to make the aluminum ion, right, it's metal, so it loses electrons. So aluminum is aluminum 3 plus. Same number of protons, right? But now if I take away 3 electrons, what's going to happen to the size of the atom? By analogy. So now I'm removing electrons. Same number of protons, but I'm removing electrons. So are the remaining electrons going to feel more nuclear charge or less? What do you guys think? More or less nuclear charge if I take away electrons, the remaining ones?
Less.
I'd say more, because again, it's kind of undiluting at this point, right? So you have the same amount of nuclear charge, but there's fewer electrons to share it amongst, right? So if there's fewer number of electrons to share it amongst, each electron is going to get more nuclear charge. So since opposite charges attract, that's going to kind of suck the remaining electrons in a little bit more, isn't it? So in fact, that's what we see. Aluminum ion is 53 picometers. So whether we make a negative ion or a positive ion matters. In other words, whether we're putting electrons in or taking electrons out. Okay, so that's kind of an interesting little aside to look at as well. All right, so the next thing we want to talk about is ionization energy. And the good thing about this is once we've kind of introduced the idea with size, the other things kind of move with it. Okay, so again, just reminding ourselves about ionization energy. I'll do it for magnesium here. So I've got to take a gas phase magnesium atom. Okay, and what I'm going to do is I'm going to make a magnesium 1 plus ion out of it, still in the gas phase, because ionization energy just means taking 1 electron out. And then you're left with that extra electron there. Okay, as I mentioned in the video, this is going to be usually an endothermic process because I have to put energy into the atom to pull the electron out, because the electron normally would be fairly stable there. So in fact, what we end up getting here is 738 kilojoules of energy per mole of magnesium that I'm going to ionize. Okay, so that's endothermic. I got to put energy in to make that happen. So these things are always going to be endothermic. So again, let's kind of take a look at ionization energies. Same elements. We'll move from lithium through beryllium to boron, carbon, nitrogen, oxygen, fluorine, and then down the column, sodium, potassium, and we'll go as far as rubidium. All right, so lithium is 520. These are kilojoules per mole. It's a 520 there. Beryllium is 899. Boron's 800. Carbon's going to be 1086. Nitrogen's 1402. Oxygen is 1314. And fluorine will be 1681. So let's look at sodium. Might as well go downwards, 496. Potassium looks like it's going to be 419. And rubidium will be 403. So we have a definite trend going in that direction. As we move down the column, you can see that we're seeing a decrease in ionization energy, meaning that it takes less energy to pull an electron out. Now, general trend going across, we see that there are sort of some outliers there, but what's the general trend moving from 520 up to 1681? Well, it looks like it's getting bigger. All right, but there's a couple of oddballs there. It looks like lithium and beryllium is bigger than lithium, but oh, look, we get a little bit of a decrease with boron. Carbon gets bigger, nitrogen gets bigger, and then oxygen looks like it decreases a little bit, and then fluorine gets bigger again. Okay, so we can come back and address that. There's a couple of oddballs in there, outliers, if you will. But you see a basic trend being generated there. Okay, so why do we see the increase across the row? Well, we can sort of fall back on atomic size here, right? So the atom gets smaller. So what does that mean? As the atom gets smaller, the electron's in closer to the nucleus, so it's going to feel more effective nuclear charge because in general, that outermost electron is going to be closer to the nucleus. Closer it gets, the more charge it's going to feel. So that's one. The second thing, and this goes back to what we talked about when we talked about the ionic radius, is that we're getting an increased effective nuclear charge. Now that's partially, as I mentioned, due to the fact that the atom is actually getting smaller and the electron's moving closer to the nucleus. But it's also due to the fact that as we go across, we're adding a proton to the nucleus. So the nuclear charge is actually getting bigger as we move from left to right by a unit of charge every time. And remember, where are those electrons going? They're going into the same principal energy level, the n equals 2 level. So you're going to feel that increased nuclear charge, all right? So that's the same argument that we used when we talked about the size getting smaller. So it's really going to be a combination of those two things that gives us that increase in ionization energy as we go across. Now, what about the decrease or as we move from top to bottom? Well, again, first thing is the atom's getting bigger. So what that means is that in general, the outermost electron is moving farther away from the nucleus. So if it moves farther away from the nucleus is going to have less of a pull on it, okay? And also we can fall back on the other argument that we made before, which is that we're getting increased shielding by layers of core electrons. We'll say by layers of core electrons. Okay, so again, that's an argument we made when we were talking about the changes in size, why the atom gets bigger as we move down the column. So let's go back and take a look at those two exceptions that I mentioned. So we're talking about boron and oxygen there. So let's look at it in terms of orbital diagrams and see if we can figure out why these two things might be exceptions. Okay, so we're going to look at it from the point of view of each one having a helium core. And then we're going to do an orbital diagram so we can see the order in which the electrons are going in there. So boron is going to have 3 electrons past the helium core. So you're going to have 2s, and then we have a series of 2p orbitals we can put in there. Okay, so we've got 1, 2, and then the third electron goes here. Okay, now let's think about it. Why would you actually see that electron ionization energy go down? From beryllium, it's 899, but boron, it looks like it's 800. So why do you think it might suddenly get easier to pull that last electron we put in back out? Anybody have an idea based on the orbital diagram that we just drew?
It's unpaired.
Well, that's a good idea, but it really has to do more with the fact that we're starting to fill a set of p orbitals. Now, which one's higher in energy, a p orbital or an s orbital, do you think?
Orbital.
P orbitals, yeah, they tend to be a little higher in energy, right? In general, the electron's a little further out from the nucleus, so it's higher energy. So we're starting to fill a new set of higher energy orbitals. Okay, so if the idea is that we're going to take that electron out, we actually get a little bit of energy back relative to beryllium because we started to fill a higher energy set of orbitals here. Okay, so we get a little bit of energy back when we actually rip that electron out. It's not as hard to do, in other words. Okay, so that's the argument that we can make in that case. P orbitals are higher in energy than s orbitals are, so it's easier to remove a single p electron. Now, let's go to oxygen and see what's going on there. All right, so oxygen, we end up having a full 2s, and then we go 1, 2, 3, 4. Now, we talked about pairing energy. Somebody mentioned that just a minute ago, right? What's happening to this electron here that I'm just sticking into that p orbital? What did I have to do? Well, I had to spin pair it, which meant that now what I have to do is force it to sit in an orbital with another electron, right? So what electrons want to do when we put them in the same space? They tend to repel each other, right? So there's always going to be a little bit of repulsive energy associated with sticking a new electron into, okay, an orbital that already has an electron in it. So it's going to be a little bit nicer if I can take that back out. Now you might argue, all right, well then why don't I see the same kind of trend happening when I put that second paired electron into that second p orbital, or that third paired electron into that third p orbital? Well, what ends up happening there is that, remember, every time we do this, we're adding a new proton to the nucleus. So nuclear charge starts to win out when we get past that first paired electron there. But we can make the argument that that first paired electron is a little easier to pull out because there's some repulsion between those two electrons when I stick that second electron into that orbital. Okay, so that's a sort of a hand-waving argument we can make about that. All right. So that takes care of ionization energy. Anything else you guys want to cover there before we leave it? Any questions? And again, with these things, make sure you know what the trends are, but also make sure you have a basic idea of why the trends exist. Okay, so why is kind of important here. All right, so let's cover electron affinity then. That's the last one we have to do. All right, so we'll do that in terms of fluorine. I think that's the one we did in the video. So if I take a gas phase fluorine atom, and now I force an electron into it, we're actually doing this in mole quantities, we end up actually getting the fluoride ion, F1 minus, also in the gas phase. Now, the electron affinity in this case is actually going to be exothermic. So it turns out EA is electron affinity. The value for this is minus 328 kilojoules per mole of fluorine atom that I force electrons into. Okay, so it's an exothermic property. So what this means is that we actually get energy back by forcing an electron into fluorine. Now that's not always the case. sometimes these things do end up being endothermic. And we'll actually, I think, see one here in just a minute. All right, so let's take a look at the same elements. So working our way across, we got lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. Working downwards, I got sodium, I got potassium, and we'll do rubidium. All right, so lithium. These are in kilojoules per mole again, so minus 59. Beryllium is actually going to be positive. It's just over 0. Boron's minus 27. Carbon's going to be minus 122. Nitrogen is actually going to be plus 7. Oxygen's minus 141. And fluorine's minus 328. Going downwards, sodium is a minus 53. Potassium is a minus 47. And rubidium will be, or sorry, yeah, that's right. And rubidium will be a minus 50, or sorry, minus 46. Make sure I got the right ones there. Yeah, we're good. All right, so what's happened? It's hard to actually talk about this in terms of increasing or decreasing because we have to sort of define, well, what does that mean when I say it's increasing or decreasing? What I'm really talking about, are we becoming more exothermic or less exothermic, right? More favorable or less favorable, okay? So as we move across, notice the general trend, negative 59, and then it looks like we're going through like minus 122 to minus 141 to minus 328. So I'm actually seeing an increase in electron affinity. And when I say increase here, what I really mean is more exothermic, more favorable. So in other words, it's easier to stick an electron into the atom as I move across a row. What are we seeing as we move down? We're seeing a decrease or less favorable trend there. So it's getting harder to put the electron in. Okay, so, and again, we see a couple of oddballs there. Beryllium looks like an oddball, and we're moving more up. The other big oddball we see there is nitrogen, okay? So we can come back and talk about those two when we get there. But why would we see a general increase across a row? Well, there's really going to be 2 reasons for that. Again, the atom's getting smaller. So what's happening as the atom gets smaller? Well, again, the nuclear charge is increasing. The effective nuclear charge as the atom constricts. So what that means is that the extra electron you put in is going to feel more of that nuclear charge, so it should be easier to stick it in there. Okay, and we could make the same argument we made before, where we can say that we're getting an increased effective nuclear charge. And again, that's due to the fact that as we move across the row, we're adding a new proton to the nucleus, so we're increasing the nuclear charge. But again, with every electron we put in, all right, and even with every extra electron we put in, it's going into the same principal energy level. Okay, so it's going to feel more nuclear charge because the number of protons is going up as we move from left to right. Okay, so kind of the same arguments we used before for ionization energy, just kind of in the opposite direction. Now, what about the decrease as we move down the column? Well, the decrease, again, is due to the fact that first, the atom gets bigger. So what that means is that that outermost electron we want to stick in there is getting farther and farther from the nucleus. So if it gets farther from the nucleus, it's going to feel less nuclear charge, which means it's going to be harder to stick that electron in. All right. And again, the other argument we can make is that the effective nuclear charge also decreases due to the increased layers of core electrons. Again, we use that very same argument when we talked about ionization energy. So we'll say here we have increased layers of core electrons. And remember what those core electrons do. As I fill a principal energy level, those new layers of core electrons are going to shield the outermost electrons from the nuclear charge. Okay, that's why the atom gets bigger as we go down. So those two kind of things work hand in hand. All right. Everybody okay with that? Again, sort of the same arguments we use, just in reverse with regard to electron affinity and ionization energy. So let's go back and look at those two exceptions. We got beryllium and nitrogen. Okay, so again, we'll go back and look at some core orbital diagrams here. So nitrogen is helium as well, helium core for both. Okay, so I have a 2s and a set of 2p's over here. That's true for both. All right, so in the case of beryllium, here's what we got. Beryllium has a full 2s orbital. But now what I'm doing is I'm putting a new electron in. Now notice where it's coming into. So this is the new electron coming in. It's coming into a p orbital. But what did we say before about p orbitals when we start to fill them? Oh yeah, p orbitals are higher energy and further away from the nucleus, aren't they? So if I start to fill a set of p orbitals, it's actually going to cost me a little bit of energy to put that extra electron in there, given the nuclear charge on the beryllium atom. Okay, remember, I'm not increasing the nuclear charge. What I'm doing is I'm shoving a new electron in here, and now I got to shove it into a higher energy orbital here. Okay, so that's going to cost me some energy. All right, so that's why we actually see that upward spike of endothermicity when we actually stick that extra electron into beryllium. Let's look at nitrogen. So nitrogen looks like this. So now what I need to do is I need to stick a new electron in there. Now I've got a full set of p orbitals there. Well, not full, half full set of p orbitals there. And now I've got to suddenly put a new electron in here. Oh, that's costing me energy. Why is that costing me energy? Well, it's the same argument we made before, right? Whenever I have to actually stick a new electron in there for a given nuclear charge, it's going to cost me energy to put it into an orbital that already has an electron in it, okay? Because now I've got to overcome, the repulsion between those two electrons. All right, so that's why I see that spike with nitrogen going up to the endothermic value there. Then by the time you get to oxygen, okay, you're actually putting another electron into that second orbital. But again, nuclear charge is winning out at this point. So that's why we go back to the exothermic realm again. All right, does that make sense to everybody? Any questions you want to ask about any of this business regarding trends here? Okay, so we got a few minutes. Let's just see what we got over in Chem 101 here. I think I got some trend stuff to do here for practice. Let's check it out. Here it is. Let's just see how far we get with this.
Do you mind scrolling up to the top to see the first part of the print?
Yeah, just tell me when you want me to stop. I can go all the way to the top if you want.
Yeah, yeah, right there.
You're welcome, no problem. Don't forget, guys, I won't see you on Friday, right? Because Friday is a radar rest day. So no class, no quiz. All right, just a couple reminders, folks. Just remember to watch the next video for Monday, and we'll just do a regular 5 for 5 quiz on Monday. So you don't have to worry about a big Friday quiz this time. All right, so keep working along on this if you like. You have a few minutes left if you want to use it. And if I don't see you, have a wonderful weekend and have a very restful radar rest day, guys.
Thank you.
All right, see you soon.
Thank you.